Again, hopefully you'll have looked through those questions and gotten many of the right answers. Now, I want to present to you three different calculations which allow us to arrive at radon concentrations. And while I personally have not seen them on the written exams, does not mean that these kinds of calculations might not be on there. However, I don't want to stress too heavily that you should be able to do these. But there are some comments I want to make about the calculation which I think will offer some physical insight to you into how the device works. And that information hopefully will serve you well. Now, the first calculation I want to demonstrate is the one that is used for determining radon concentrations when you're using an electret, such as this EPIRM. Remember, what you do is you simply open up the EPIRM, you expose it for a prescribed number of days this way, and when you're done at the end of the number of days, you close it up. Of course, you will have read the voltage on the electret before you deployed the detector, and again, you would read the voltage again. We saw that earlier on when we were looking at instruments. And so the information you get typically is the kind of electret system you were using, and the voltage difference, and the number of days exposed. So let's take a look. For example, if the voltage difference here that we get in a particular exposure were 70 volts. All right, that's the difference in the voltage. And let's suppose the number of days that it was exposed was 4.2. Now, the concentration is calculated with the following equation, that the concentration is equal to the voltage difference. Now, you should be writing all of this down, divided by the time exposed. I guess we should extend this a little bit, times the calibration factor, which the manufacturer will have to give you, minus some background. Remember, we talked about background being the gamma radiation that strikes the detector while it's deployed. The calibration factor for this particular EPIRM unit that I'm holding in my hand here, the calibration factor I see is 2.2. So let's calculate the concentration then. The concentration is the voltage difference, which is 70 volts, divided by the time exposed, which is 4.2 days, and again the calibration factor, which is 2.2 in this case. And I'm going to worry about the background in a minute. So I just carry it along with me. Now, 4.2 times 2.2 is 9.24. And then again, we still have minus the background. And so 70 over 9.24 is 7.58. Let's call it 7.6 minus the background. Now, so the concentration is going to be 7.6 minus a certain amount due to background. In other words, the background gamma radiation is what has contributed a little bit to this voltage difference. Now, how do we deal with that? Well, what I'm going to do here is just repeat what I've got on that first page and write down the concentration. This is what we just had, is 7.6 minus the background. Now, how do we determine the background? If you will recall, depending on the chamber type that you're using, depending on this particular chamber, and the manufacturer will tell you which one you have, you're going to subtract off a certain amount for the gamma radiation that exists. Let's assume for a moment that we have, if we have 10 micro-Roentgens per hour of gamma radiation, and what we're going to subtract, therefore, we're going to subtract off 0.8 picocuries per liter for every 10 microroentgens per hour. In other words, we're getting 10 microroentgens per hour, so we're going to subtract off 0.8 picocuries per liter. If we had 20 microroentgens per hour, we'd subtract off twice this. And so our concentration then becomes the 7.6 minus the background, which is 0.8, leaving us with 6.8 picocuries per liter. And that's our resultant concentration. Now let me just return to the top of the calculation here to show you how the concentration is calculated. Again, if we look this over, notice that it depends on the voltage difference. The bigger the voltage difference, the bigger the resulting concentration. If you have a fixed voltage difference, for example, in this case, we had a 70-volt voltage difference, and it occurred over 4.2 days. Suppose we'd have had that same voltage difference over 10 days. The concentration would be much less, because we'd be dividing by 10 instead of 4.2. So you should recognize that the longer it's exposed for a given voltage difference, the lower the concentration you're going to get. That should make sense. It took longer to get the same voltage difference, and therefore the concentration must be less. And the background, of course, has to be subtracted, and I'm really just reiterating myself here. The background has to be subtracted, and again, depending on the chamber you're using, you're going to subtract somewhere on the order of 0.8 picocuries per liter for every 10 microroentgens per hour, which in this case gives us 6.8 picocuries per liter. So the information you need to do the calculation clearly is the voltage difference and the time it was exposed. You must get the right calibration factor from the manufacturer, and you must subtract off the appropriate amount of background, as we have done in this example. Now, I've also added a few questions when we go on a little bit here, a few questions, and you will exercise yourself in this kind of problem. Again, not to make you an expert at doing this kind of calculation, but rather just to show you the trends of what parameters have what effect on the concentration. Okay? So now, let's go over to the second type of calculation that I would like to demonstrate. The second type of calculation I want to demonstrate deals with grab samples. And if you recall, in a grab sample, typically you will take a Lucas cell, and we've seen these, and they have, of course, the white scintillating powder inside, and I'm putting the cover on it just to protect it, and we draw air into the vial. Sometimes we have a pump, and we pump air through, and so that we get the air in the vial in the cell, in the scintillation cell, to be the same as the air in the room we're trying to measure. And then we seal it off, and after it's sealed, after a given amount of time, we put it in front of a phototube, and the phototube acts like the human eye and detects how much light is being given off by the scintillation cell, and we count up the number of pulses of light. And from that, we determine the concentration. Now, in this calculation, which is a little more laborious than the one for electrets, we're looking again at a grab sample, and we are looking at the use of a scintillation cell. Now, the formula that is used is simply this, that the concentration is equal to the counts per minute of the sample minus, and again you should be writing this down, minus the counts per minute of the background divided by the efficiency of the system, and then corrections for time. And the corrections are a C divided by A, and then 1 over V being the volume of the cell that was used. Now, in this case, we have to get the background counts per minute, and the way we do that is we take the phototube with a fresh scintillation cell, that is a scintillation cell which has been purged with nitrogen air or brand new, has no activity in it at all, and we put the scintillation cell in front of the photo tube, and we count that up for a prescribed number of minutes, and we see so many counts per minute. Now, that's from a fresh cell. So in that fresh cell, suppose that the background came out to be, I'm choosing easy numbers for myself, 10 counts in 10 minutes, which is 1 count per minute. I choose easy numbers for myself, and then in the problems that you'll do, we'll make those a little more challenging for you. So we have a background of 10 counts per 10 minutes, so that's 1 count per minute, and that's the background here. Notice we do have to subtract off the background. Suppose now we take the Lucas cell, more typically called the scintillation cell now, in which we've drawn the ear from the room, and we put it in front of the photo tube, and we count up how many counts per minute we get from the ear sample. And suppose that when we do that, we get from the sample, suppose we get 1,200 counts in 120 minutes. That gives us, of course, 1,200 over 120 is 10. Note the ease of these numbers. Counts per minute. So now we have the sample count per minute, and we have the background counts per minute, a 10 and a 1 here. The efficiency of the system, that is the scintillation cell plus the photo tube, you see for every picocurie of radiation you have in the scintillation cell doesn't mean you're going to see 1 count per minute using the photo tube. And generally it's different from that. And in this particular case, the efficiency, at least for this example, is 4.62, and it's counts per minute per picocurie. What that means is that for every picocurie of radiation in the scintillation cell, the system of the phototube plus the scaler that adds up the counts, the system sees 4.62 flashes of light. Altogether, we see 4.62 flashes of light for every picocurie of radiation in the scintillation cell. That's what the efficiency means. So now we have this, this, and this, but we have not corrected for the time. And that's what the C and the A will do for us. Now the reason we have to correct for the time is because suppose that you left this scintillation cell in the back seat of your car. And if you leave it in the back seat of your car for a day or two, obviously the amount of radioactivity will have diminished. So we have to correct for that. And the correction factors are given in Exhibit 2-1, which I have on display over here in this visual. You also have it following, it should be the very next page in your workbook, and you see there are corrections for parameter A and a correction for parameter C. There's A right there and C right over here. And here's the time. Now A is the correction for radon decay from the time of collection, and you can see the rest of this sentence on your sheet, from the time of collection to the start of counting the sample. Now in this particular example, let's let that time for, let me see, that's A, the time for A, B, let's let that be 4 hours. Okay? Time for A. Now that's the time that passed from the time I took the sample to the time I brought it to the lab and started the counting. Okay? So it was 4 hours from the moment I finished taking the sample and brought it to the lab for counting, or brought it to that instrument for counting. That's 4 hours. Now, if you look at the chart over here, under A, under hours, and look at the time. Now, just come down the time, come down to where it says 4 hours, and then sweep over to the value of A, 0.97026. So just read it right off the chart, 0.97026. So A is 0.97026. And that corrects, when we place it into this formula, that will correct for the time it took for us to get it to the lab. Now, we're going to count this sample not for just a few seconds. We're actually going to count this sample. In my example here, we're going to count it for a period of 2 hours. 2 hours. And that is, we're going to put it on this photo tube for a 2-hour period. And when we're done, we're going to look at the total counts and the total minutes, and we're going to get a counts per minute. And you can see it was counted for 2 hours. It's 120 minutes. So it was counted for 2 hours. Now, during that time, the count rate will drop off because some of the radon is going to be decaying. And we have to correct for that as well. And the way we correct for that is using this term C that you see right here. So you come down to the time, 2 hours, that's the count time, and you see C is 1.00757 because we counted for 2 hours. So in that case, jotting that down, C is 1.00757. We have everything in the formula now except for V, and V is the volume of the scintillation cell. Obviously, if we're working with a really big cell getting a certain amount of radiation, that concentration would be less than working with a little cell and getting the same amount of radiation. So the volume of the cell is important. And the volume of this particular cell, that volume is 0.17 liters, okay, about 2/10 of a quart roughly. And now we're going to take and plug all of these numbers into this formula. So let me rewrite the formula here. Again, we're looking at the concentration equals the counts per minute of the sample minus the counts per minute of the background. Always have to take background into account. Divided by the efficiency, and then we multiply that by C over A, and then again 1 over V. And I'm just going to plug in all the numbers now. The counts per minute of the sample was 10. The counts per minute of the background was 1. The efficiency of the system is 4.62. The correction factor C was 1.00757. The correction factor A was 0.97026. And then it's 1 over the volume, which is 0.17 liters. And so now 10 minus 1 is obviously 9, divided by, and I'm going to just do this division now, 9 divided by 4.62 is 1.95. So that's everything in here is 1.95. And then I can reduce this fraction, 1.00757 divided by 0.97026 equals 1.04. And so everything in here comes out to be that number. And then 1 over 0.17 is 5.88. And that is, of course, everything in this square brackets. And now if I multiply those three, I get 11.9 picocuries per liter. And so the calculation, as you can see here, we've done in a matter of 2 or 3 minutes. It's not particularly long. But note some of the things in the equation. The efficiency is the efficiency of the system. That's the number of counts per minute it sees per picocurie of radiation in the cell. Note where the volume of the cell is. It's in the denominator because we want to get picocuries per liter. So we want the liters downstairs in the bottom of this fraction. And so that's where the volume goes. And we do have to correct for the time, the total time. That is, part of that time, the C, is the time for the time that passes during the count period, that 2 hours of counting on the system. The A is the correction for the time it took to get it from the home to the sample, to the laboratory, in effect. So we have to correct for all of that in the calculation of a grab sample. And that's the way a grab sample would work. Okay? And again, I've got one or two problems following that I hope won't give you too much trouble, but I would like you to exercise your understanding of this equation in those problems in just a few minutes, and I'll let you know when it's time to do those problems, okay? In this third and final calculation I'd like to demonstrate to you, it's going to be based on the Kuznets procedure of determining working levels. Now, what that should tell you is if we're looking at working levels, we're looking at daughter products, which are solids. And so typically what we do in that case is we draw air across a filter, and then the daughters will collect on that filter, and we will then look at the radioactivity being emitted by that filter paper. So fundamentally what you have here is you have a hose through which we will draw air across a filter holder, like so, and then the hose continues on this way, and we draw air across the filter paper that's in here, and it collects the daughter products. Afterwards, we remove the filter paper. Here's the filter paper edge view, and we put it in front of a detector, and we count up effectively how many counts per minute we're going to get off of that piece of filter paper, and we're going to interpret that into daughter product concentrations, working levels. And the formula that is used is that the working level that we get is equal to the net counts, which we call C, divided by some coefficient, KT, divided by the volume of air that we drag across the filter paper, and divided by the efficiency of the system. And I'm going to talk about the efficiency in a minute. First, let me get this value C, and this value C is equal to the sample counts per minute minus the background. And to get the background, what we do is we take a perfectly clean piece of filter paper, brand new, and we put it in front of the detector, and we count it up for a few minutes. Now, in this example, suppose that the background gives us 3 counts, that is from a clean filter paper, in a period of 5 minutes. That is, we count it for 5 minutes, and during that time, we see 3 counts altogether. And of course, that is 0.6, 3 over 5, 0.6 counts per minute. So the background for this system in this example is 0.6. Now, the next thing we can get is the efficiency, and here, rather than the manufacturer telling us the efficiency, we have to figure it out ourselves, and that's a little more laborious. Now, remember, the efficiency is just the number of picocuries, the number of counts per minute the system will see for every picocurie or for every working level of daughters on the filter. And so what we do is, typically you get a standard piece of filter paper, if you like. And this is one way to do it. And suppose we get a standard that we know has 2,430 decays per minute. That is, on that piece of filter paper, let's assume that we have 2,530 atoms decaying every minute. We know what the decay rate, that's what the manufacturer who sold us the standard made it out to be. 2,430 decays per minute. And if we count this for 5 minutes, let's suppose that we get 5,985 counts in a 5-minute period. Now, we're not going to see all of these decays because, for one thing, some of the decaying products are going to come off in this direction. Some of the radioactive decays come off in that direction, and our counter's never going to see them. So we're going to see somewhere around half of them. And this example will make that come true. We have 5,985 counts. We put the standard filter paper on it in a period of 5 minutes, and of course that comes out to be 1,197 counts per minute. Now let me just continue that here. You're getting 1,197 counts per minute. But not all of that is due to the standard. 0.6 of that is due to background. Now, it's not much, I have to admit, but we're going to take it into account anyway. We have it. And so the efficiency, we can get the efficiency of this system is going to be, it's 1197 minus that 0.6, divided by the total number of decays per minute of the standard, 2430. In other words, we're not getting all of the 2430, we're really getting 1196.4 of the 2430 decays per minute. And if you work this number out, you get 0.49, almost half. That is, the efficiency of this system is 0.49. And in order to get that efficiency, you have to have had a standard available to you. And you must also have been able to determine the background earlier on. Now, let's further suppose that the sample volume, I'm looking at the V in the equation for working level now. Let me bring that down here. I'm going to look at this V for a moment. What is that volume? Well, that's the volume of air that we have dragged across this filter paper. And how do we get that volume? Well, the sample volume, we have a flow meter, and let's assume that it's flowing at 4.4 liters per minute for a period of 5 minutes. We let the flow occur for a 5-minute period, and if you do that, of course, you find that that is 22 liters. So the volume of air that we dragged across the filter is 22 liters. And now the final correction is the correction for time. That is, you take the filter paper off of the machine, you bring it over to the detector, and during that time some of the daughters decay, and if you remember, the half-life of the daughters tends to be pretty short. So we have to take that time into account. And that's what the KT factor will do for us. Let me just rewrite the equation here so we have something neat to look at. Again, the working level is, that's the net counts over KT, V, and E. And actually we have everything except KT. And for that, all we have to do is determine how much time passed between the time we stop the flow meter and remove the filter to the time we put it on the monitor that's going to measure the counts per minute off of that filter paper. Now, for this purpose, let's let the time between, and I'm going to explain this to you, be 45 minutes. Now what I mean by this time between, that's the time that passed from the moment we stopped the flow meter, or stopped the flow through the filter paper, that is from the moment we stopped taking our sample, to the time we put it on our detector. That's 45 minutes. And from that we can get the KT factor, and well, with one more piece of information. Let's let the count time, then we're going to count for 10 minutes. If the count time is 10 minutes, then even during this 10 minutes, some of the daughters will have decayed. So what correction do we use? What time correction do we use here? And if you look at the chart in the very next page, you will see that we have time listed here, and then we have the correction factors listed here. Now what time should we use? Well, we should use the time, the total time that passed from the moment we removed the filter from the sampler to the middle of this time period, this 10-minute period. That is, it was 45 minutes from the time we removed the filter paper from the sampler to when we put it on the detector, and then we counted for 10 minutes. That's an extra, halfway through this 10 minutes is an extra 5 minutes. So the total time is 50 minutes to get to the midpoint of the count time. And if you come down here, time 50 minutes, the correction factor is 130. And so now we have all of the variables that go into the equation. KT is 130 to get the working level. So we get the working level. Now remember, this C is the net counts. And so what we have to have is, let me just write that as the sample counts per minute minus the background counts per minute, all divided by KT, which is 130, the volume, which was 22 liters, and the efficiency, which was 0.49. Now, when we still have to count the sample. I have not given you that information yet, but let's suppose that when we count the sample, when we counted the sample, that is, we put the filter paper on and we counted it for that 10 minutes, let's suppose that we got 560 counts in that 10 minutes. So the sample is 56 counts per minute. And that's the number we're going to put up here in the sample. Background, we already know, is 0.6. So let me write this equation again here. The working level comes out to be the sample counts per minute, right here, which is 56, minus the background, which we determined to be 0.6, divided by the time correction factor, the volume of air drawn over the filter paper, and the efficiency of the system. Now 56 over 0.6 is of course 55.4, and divided by 130, 22, and 0.49, if you work that out, comes out to be 0.04, and so the working level is 0.04. Now that's a pretty ornate calculation all in all, because we have one difficulty, and that is we have to get the efficiency of the system on our own. It's not told to us by the manufacturer. I want to look at just one other parameter here that has an effect. And let's take a look at the volume in this particular Kuznets procedure. Suppose the flow meter were reading too low. Now I'm just considering this equation here. And if the flow meter is reading too low, that means the volume we get will be too low, regardless of how many minutes we run it for. And if the volume is too low, we'll get a working level that's going to be too high. And so the effect of the volume is very large on the results of the working level. And you need to recognize that that the flow rate is very important in determining the concentration based on the Kuznets procedure. Again, there are a few questions and one or two calculations that I'm going to ask you to do, which follows this last calculation, and then return to the video at this point. So please deal with those questions as we have done in the past, and return back to the video at this point. We'll now begin part 6 of this program, and this part deals with the Radon Measurement Proficiency Program that the EPA has created and continues to support. Now the purpose of this program, as you see here, is to provide opportunities to demonstrate proficiency. This is so that those of us who are doing radon testing or laboratory work can demonstrate on a national level that we are quite competent at doing that. And also, the purpose of the program is to assist consumers and state agencies in finding people who can do these kinds of measurements competently. There are two kinds of measurement services that are allowed into the EPA RMP program. The first one is called the primary measurement service, as opposed to the secondary measurement service. And what distinguishes them is that in the primary measurement service, those individuals or companies that read or analyze measurements and yield results are called primaries. That is, if you're using a continuous radon monitor, whereby you actually get the radon concentration values right there, or if you're a laboratory analyzing charcoal cans, then and coming up with the radon concentration in picocuries per liter, then you are a primary. If what you're doing is deploying the detectors but not reading them to get the final concentration, then you will be listed as a secondary measurement service. Now we see here that primary measurement services are required to have a quality assurance plan. That is a prescription by which you do your measurements and come up with results. They will be listed by the EPA. There will be a long listing of individuals or companies who are noted as RMP proficient, and they're listed by device. Now what that means if you're a primary, is that if you're using charcoal cans, for example, in this case I'm holding up a 4-inch can with a diffusion barrier that you may or may not be able to see. You could be listed, if you use this can, as one who uses 4-inch cans with diffusion barriers. You are specifically listed for that device. You're not listed for EPIRMs. You're not even listed for a 3-inch can without diffusion barrier. It's specific to the device that you're using. And if you are a primary, you must be tested periodically in a radon chamber. Now, the chambers that are currently available for this are, one is in Montgomery, Alabama, and the other is in Las Vegas, Nevada. And some of the devices can be mailed in, others must be carried in by the operator of that device, which of course complicates the issue for primary measurement services to some degree. There may be other radon chambers to be opened up as the years go by, but currently the two available are in Las Vegas and Montgomery. And fundamentally what happens for primaries, again, suppose you're using charcoal canisters, is you would send 4 of these charcoal canisters down to the chamber, and for charcoal canisters, I believe you can mail those in. They're exposed into the EPA's radon chamber and returned to you. You analyze them, and you're supposed to come up with the right result, plus or minus 25%. And I'll talk about that percentage business here in just a minute. And so the idea there is that primaries have to be able to show their proficiency regularly in the R&P program by sending their detectors to the radon chambers. Now, secondaries, as you see here, must use primaries to determine results, and they are listed by method. That is that a secondary service, that is the individual who goes into the home and deploys the detector or deploys perhaps an electret measuring device, that individual will be listed as a secondary because he does not come up with the result, the actual radon concentration later. But he is required, if you're going to be part of the R&P program, he is required to use someone who is a laboratory that's listed as a primary. That is a laboratory that has gone through the R&P program and shown that they can satisfactorily come up with the proper results. Also, the secondary is listed by method. So if you're listed by activated charcoal, the acronym for it being AC, then you can use a 4-inch can with a diffusion barrier. Without a diffusion barrier, you can use a 3-inch can. Any device that comes under the activated charcoal method and that has satisfied the R&P program through some primary lab. You're not listed by device, you're listed by method as a secondary measurement service. Now, further requirements of the secondary measurement services is you must have a quality assurance plan, you must use listed devices and listed primaries, that is primaries who have passed the R&P program. You do not need to be tested. Now, unfortunately, this does not mean you can skip the R&P written exam. It just means that you do not have to send your devices to the radon chambers in order to demonstrate your proficiency in coming up with the proper results. Now, how do you get into the R&P program? Fundamentally, you must file an application. And if you're a primary, if you intend to be a primary, you have to have one application per brand, model, and type of equipment. If you're a secondary, you need one application per method used. So if you're a secondary, all you have to do, and you're going to use activated charcoal, you just file an application that says you're going to use activated charcoal, ACs. And of course they know that means different kinds of canisters. And that's all your application has to comprise. That is just the activated charcoal. But if you're a primary that is coming up with the radon concentrations themselves or the working level values themselves, then you would be listed, you would have to have one application for 4-inch cans with a diffusion barrier. You would have to also have another application for 3-inch cans, for example, without a diffusion barrier. Or if you're going to use continuous working level monitors, let's say, and you're going to use the one by Eberline and the other one by Pylon, then you have to have one application for the continuous working level monitor by Eberline and a separate application for the one by Pylon. So you can see that for the primary, their application is by type, very specific type of equipment. For the secondary, it's by the method. Now, there are two types of requirements in the RMP program. The first of which is the continuing requirement. That is, if you're already in the program and you're continuing in the program, there are certain requirements. And there is a set of requirements in order to enter the program. There's quite a few of the requirements, actually, and I think I have a method by which you can remember most of them without getting too caught up in the whole issue of memorizing. You see here the entrance requirements. Obviously, now if you just think about it and use common sense, obviously there's got to be an application. You must have developed a quality assurance plan. Now notice this, develop and implement. Obviously you can't have implemented the plan yet, or you should not have implemented the plan, because you haven't gone through the RMP program yet, even as a secondary. So, but develop and implement, because the word develop is there, means since you must have a QAP, this must be part of the entrance requirements. Same for have and use your SOPs, standard operating procedure. Now the standard operating procedure is really a very practical application of your quality assurance plan. They're very closely related. You must, in all cases, comply with requests for information. If the EPA calls you or sends you a letter saying how many tests did you do this year rather, then you're to comply with those requests for information. That makes sense. Follow the EPA instructions. Gee, that makes sense. And if you're a primary, you must pass the radon measurement test, meaning simply that you must get your detectors through the radon chamber and come up with the right results. That's if you're a primary. Of course, you don't have to do that if you're a secondary. Now, those things hopefully make sense. And those are the entrance, some of the entrance requirements. In fact, I believe those are all of the entrance requirements. Now, for continuing requirements, I've listed those additional ones. You're to notify the Quality Assurance Control Officer at the RMP program of any changes. If you change your mailing address, for example, then you're to notify them that you have changed your mailing address. That makes sense. Again, develop and implement a quality assurance plan. Well, when you entered the RMP program, you already developed it. But because it says develop and implement the quality assurance plan, this becomes part of the continuing requirements as well. Same comment for have and use SOPs, standard operating procedures. And of course, you will follow the protocols. Anybody who's in the business is going to follow the protocols. There's a modest amount of protection in doing that. Further continuing requirements are listed here. You will follow the EPA guidelines for advertising. You are not permitted, for example, to advertise that the EPA has certified you if you've passed the RMP program, because the EPA does not do certifications. There are only certain statements that can be made regarding advertising and quoting EPA. So you will follow the EPA guidelines. You will follow the guidelines in reporting results. And here, I want to point out to you that when you report your results on radon concentrations, for example, the house got 4.1 picocuries per liter. The guideline is to report 1 decimal point. That is, you're to report 4.1, not 4.16723, but just 4.1 picocuries per liter. So radon concentrations in picocuries per liter are reported to 1 decimal place. Working levels, however, since they're obviously much smaller, working levels are measured to 3 decimal places. So typically when you do a working level measurement, you will report them out to, say, 0.003 working levels or 0.023 working levels. You will always report it with 3 decimal points. You will also, continuing on here, comply with requests for information, follow EPA instructions. If you're a secondary, you're to use RMP primaries only. And if you will pass the radon measurement test, that is, go through the radon chamber if you're a primary, periodically. Now, in the RMP program, if you're a primary and you send your detectors to the radon chamber, how many of them do you send? Well, typically, I note here, you send 4 of your detectors. If you're using charcoal cans, you send 4. If you're using EPERMs, you send 4. If you're using alpha tracks, you send 4. and you have to get all 4 correct. However, the ones that are exceptions to this, and I think these are not too hard to remember, the continuous radon, the collapsible bag, continuous working level monitors, and the RIPSU units, all of those you have to send only one of these devices. In fact, in some of these devices they're not allowed to be mail-ins, you actually have to bring them down yourself. And that makes sense that those would only be one, because how many of us would have 2 continuous working level monitors? They're a fairly expensive device. And so one is allowed in those 4 cases. Now, the way to get through the RMP program, again, if you're a primary, and we need to be familiar with this, if you're a primary, is remember you're sending in, let's say we're doing it with charcoal cans again, you're sending it in, you're sending 4 of them in. And the requirement is this, that you must be within 25% of the correct result in all 4 measurements. If you are, if all measurement errors are less than or equal to 25%, you will be listed. That's it. Effectively, the issue for you is over, at least for the year, until the next cycle comes up where you have to do it again. And remember, this again is only for primaries. Now, if all the measurement errors are not within 25%, in other words, no, the measurement errors are not within 25%, then the question is, are the measurement errors all within 50%? Now, if they're all within 50%, you can be retested. And in that case, you sure do hope that in the retest, as you'll see, that the final results are within 25%. Now, what retest means is that if you sent your 4 cans in, and they're all within 50%, but not within 25%, then you can resubmit 4 new cans. You don't have to reapply or go through all the paperwork all over again. You can typically resubmit in very short order the 4 new detectors to try to get within 25%. Now, if your measurement errors are more than 50%, then you've got to reapply to the program and start all over again in the application process, which of course is long, a fairly long, time-consuming process. Let's go on now with the area of assuming that all of the values that you got were within 50%. So you resubmit perhaps 4 new charcoal canisters, and now the question is, are all the measurement retest errors within 25%? If they are, then you'll be listed, and that will end the issue for you, at least again for that year. If not, you must submit corrective action and reapply from scratch all over again. So you have to go through the entire application process for the RMP program, including what corrective action you've taken to explain away the large percentage errors. Give you an example of this. Let's take a look here. Suppose you have measured values given here. In other words, all 4 detectors were put into the radon chamber at these different concentrations. In other words, these were the chamber values, 7.2, 18.3, etc. And you come up with values as indicated here. Note here the percent error in each case, 14, 10, 29, and 15. Now, this is suitable for a retest. It didn't pass because one of them is greater than 25%. If this one had been 25 or less, then this particular individual would have passed the RMP test. But because one of them, the 29%er, is more than 25%, this individual would be suitable for a retest. And hopefully during the retest, they would get within 25%. If not, in the retest, then they would have to restart the application process. As a second example, suppose you send or you bring down a continuous radon monitor, and the target value that's put into a radon chamber at 35 picocuries per liter, and the measured value is 15.7. Here the percent error is 55%. As you see, not eligible for a retest, must reapply from scratch. Now you'll note on your very next page of your text there's an array of questions, and as is usual, I would like you to deal with those questions as we've done before. This will end part 6 of the program, but when you're done with those questions, you've checked the answers, return to this part, and we will continue on with part 7 of the program. This is part 7 of the program, and in it we will discuss the Radon Contractor Proficiency Program. EPA has a proficiency program for radon contractors, and pretty much most contractors in the EPA, most contractors doing radon mitigation will become part of this, or become members of this RCP program. Now, fundamentally, if we look at the standards required of the contractors, as I have listed here, the contractor is required to review and assess prior measurements. Now, let me just talk about that for a second. The reason the contractor is at the house to do a radon mitigation or give an estimate of a radon mitigation is because there's a measurement that indicates that it needs to be mitigated. Now, if you're in the RCP program, you're required to look at that measurement and see if it was done in accordance with the protocols. And if you suspect that it was not done in accordance with the protocols, that contractor will be required to recommend that the house be retested before mitigation begins. Doesn't mean the house has to be retested, but the contractor must recommend that it be retested. The RCP program also requires a visual inspection be done before the mitigation work be started. Obviously, it's unreasonable for me to call a radon contractor and say, look, I've got a radon problem in my house, concentrations, let's say 10 picocuries per liter, and I'd like you to come down and give me an estimate on mitigating it. If the contractor says to me, okay, it's going to be $1,500, and we'll put a sub-slab mitigation system in and we can start Wednesday, how would that be? That would not be very satisfactory to me. Reason being, the guy hasn't even seen the house yet. How does he know that that's going to work? That may well turn out that sub-slab will be the system to use, but how does he know that ahead of time? So a visual inspection, at minimum, is required for all of those who are taking part in the RCP program. The contractor also advises whether or not to use temporary measures. Now, in the case of temporary measures, you might go and someone's using a recreation room in a basement and there are some windows and the concentration in that room could be, let's say, again, 10 picocuries per liter. And you might suggest, well, look, we can't start until a week from Thursday to do the mitigation. What I recommend in the meantime is you leave the windows open, or maybe we put a fan in the window, something like that. So the contractor will be required to advise whether or not temporary measures should be used. However, as you see here in the last item on this visual, you may not use temporary in place of permanent measures. That means you can't say, well, put a fan in the window and that solves your problem, give me $300 and I'm out of here. That would be inappropriate, and it is not acceptable according to RCP standards. Furthermore, if a temporary system is to be used in some way, it must be labeled as temporary, as you see here. You have to label it as a temporary radon mitigation system, and that you have 30 days within which to install a permanent system from the time you install the temporary system. 30 days. So these are the kinds of things we need to remember for purposes of the RMP exam. It's interesting that the RMP exam, the Radon Measurement Proficiency Program, requires us to know something about what goes on in the RCP program. That is not unreasonable. We should know something about what the other individuals who dovetail into our measurement area are doing and what they're required to do. Now, again, in accordance with the RCP standards, that is, if you're going to be part of the RCP program, there is a requirement that you give the client certain kinds of information. And I have listed them here. You must show them your RCP ID number. If you're a member of the Radon Contractor Proficiency Program, you will receive a photo ID card with a number on it. The client is supposed to get that number. You're supposed to tell the client the entire scope of the work. That is, how much is going to be done, where will the work be done, if you're putting sub-slab in, where will the pipes be put into the slab, etc. The client is also supposed to be told a statement of any known hazards of the materials used. Suppose you're using some cement that gives off a toxic gas for 12 hours. The client has a right to know that, and the client should be told that. Further, the client will be told that you are, as a contractor, complying with the EPA requirements and that you are complying with all the codes, all the suitable codes, local codes, construction codes, electrical codes, etc. Those are the kinds of information that the client is supposed to get. Beyond that, there's two other items that I think you should be familiar with that the client should get, and one is the client's to be told what the future maintenance is going to be. If you put a sub-slab system on it, maintenance may be the replacement of the fan after 10 or 12 years, or certainly it will be to make sure that the exhaust port of the mitigation system is free and clear of debris and leaves and squirrels' nests, etc. Also, the client is to be given an estimate of the installation and the operating costs. The client has a right to know an estimate of what it's going to cost for the entire mitigation system installed and how much it's going to cost on the average to operate that, typically on a yearly basis. In regards to the system installation, let's take a look at some of the requirements that the RCP program puts on the contractor regarding system installations. Here you see temporary systems should be made permanent within 30 days. Actually, we've seen this already, clearly something you want to remember. The mitigator complies with all laws and codes. That makes sense. That's an easy one to remember. Now, these MSDS sheets, these are the material safety data sheets. They're to be given to all workers, and what they are is a list of the known hazards of the different products that are being used in the mitigation. Again, suppose you're using a caulking compound that should not touch your fingers, and if it does, it should be washed off in some way. That kind of information would be listed on these MSDS sheets, and that kind of information is to be given to every worker. Also, under system installation, the RCP program requires that a monitor must be installed, typically in a sub-slab mitigation system, in one of the rising pipes that comes from the slab and goes up and eventually ends up out of the house, guiding the radon gas out. Typically, a small hole will be drilled and a manometer will be placed in there with a colored liquid in it to indicate whether or not the system is under depressurization. These are just $3, $4, $5 items installed in a matter of 1 minute, and they're easy to put in. Monitors are required in accordance with the RCP standards. Further requirements in the standards is that every visible portion of the mitigation system is to be labeled as a radon mitigation system. So if you have, again, a sub-slab mitigation system, and you have 2 or 3 suction points and 2 or 3 pipes, every pipe is to be listed as a radon mitigation system. Also, there must be a central label placed on the system. Now, what central means to me could mean something different to you, but to me it would indicate that probably by the circuit breaker for the radon system, I would put a label there which indicates the system description, the contact name and phone number, and that must be legible from 2 feet. Now, you could also put a central label like this, which is really almost a business card, really. A central label fastened to one of the suction pipes that is centrally located in the basement, perhaps right next to the monitor, because the monitor needs to be put in a visually accessible place, something that you would walk by regularly. And that being the case, perhaps that would be a good place to put the tag as well, the central label. Also note, another requirement on RCP contractors is that system fans are not to be placed in conditioned space, in a basement, or on a crawl space. Now, the reason for that is that if the fan should become damaged or fail in some way, you remember that the radon gas beneath the slab can easily be in the order of hundreds of picocuries per liter. And you're drawing that gas up through the fan and outside the house. If the fan should break, or if one of the collars should come loose, then what you're actually be doing is drawing off hundreds of picocuries per liter of radon gas and dumping them, say, in a crawl space directly beneath the living space. And that's obviously not a good thing to do, because that radon will percolate up into the living area. So fundamentally here we see system fans not to be placed in conditioned space, that's heated and air-conditioned space, in the basement or in a crawl space for exactly the reason that I have mentioned. Just a few more requirements on the contractor. The discharge point of the, if you have a subslab mitigation system, the discharge point has to be at least 10 feet above the ground. 10 feet from any potential opening that is less than 2 feet below the exhaust point, 10 feet or more from public or private access, and 10 feet or more from adjacent buildings. Fundamentally, what we're being told here is that wherever the exhaust point is for this radon mitigation system, it's got to be 10 feet away from any place where someone could inhale the exhaust gases. 10 feet is the key number to remember. The only complication to it, as you see here, is that if you're putting it up through the roof, which is typically the way to go, it's to be 10 feet from any potential opening that is less than 2 feet below the exhaust point. So here, if you bring it up through the roof, you should have it exhausting 10 feet away, at least 10 feet away, from even a window that would be 2 feet below this point. If the window's 3 feet below this point, then you can actually have the exhaust point a little bit closer. Still, it needs to be 10 feet away. So fundamentally, 10 feet from anything, including the one complication that it must also be 10 feet from any opening that is within 2 feet of the exhaust point. Okay, I don't think that's too difficult to remember. Another requirement of the RCP program listed here, you must ensure, you are responsible as the mitigator to ensure that the follow-up test is to be done between 24 hours and 30 days from the end of the mitigation installation. That is, you put the mitigation system in, let's say you finish it at 10 o'clock this morning, and you are responsible for seeing that a second test, a post-mitigation test, be performed no sooner than 24 hours from now and no later than 30 days from now. So obviously it's going to be a short-term measurement. The idea being that we want to see if the mitigation system is working. We don't want it done within 24 hours, but because if you were working in a basement, you probably had the windows and doors open, and so the radon may be very low to start with. So we're going to give it a day to let the house come to its equilibrium radon condition. But we don't want to wait more than a month because we want to really tell soon that the mitigation system is in fact working. The mitigator is also required, if you're in the RCP program, to recommend that the follow-up test be done independently. It does not mean that the mitigator cannot do the test. It only means that as the mitigator, I must recommend to the client that now you should do a post-mitigation test, you should have it done, and that it should be done by someone other than me. That's the requirement. And you must also, as the mitigator, recommend retesting every 2 years. You're to tell the homeowner that the mitigation system is working, it's working fine, presumably. It's working fine, and please remember that every 2 years we recommend that you do another radon measurement, just to make sure that it continues to work properly. In the area of worker safety, it's very brief, very short. Fundamentally, in the area of worker safety, it simply indicates that you are to comply with all OSHA standards. That's it. That's the only requirement under worker safety as far as the RCP program is concerned. And one relatively new item is the issue of backdrafting. It is possible when you're using a depressurization system that you could depressurize a basement enough to get the exhaust gases, say from an oil furnace, to be re-entrained right back into the house. That is, you have an oil furnace. Let's imagine we have an oil furnace here. It's working. It takes a lot of air from the basement, draws that into the combustion chamber, ignites it, and then the exhaust gases go up the chimney. But if you depressurize the basement, it is possible for that furnace to draw in air from the room, ignite it in the combustion chamber, and then have that gas brought right back into the basement. And that effect is called backdrafting. And as you see here, the requirement of RCP contractors for backdrafting is that all buildings which use combustion devices and have installed a depressurization system are to be tested for backdrafting immediately upon completion of the installation, and that any backdrafting condition shall be corrected immediately. That's the last of the requirements of the RCP program that I'm going to present to you here. And in effect, Now, on the very next page, you'll see another series of questions dealing just with the RCP program. And then beyond that, there's a sample exam, an array of questions put in the back beyond these last set of questions that you'll see. And what I recommend is this. First, do the questions at the end of this part of the program. That is the Part 7 questions. Check the answers, make sure you have those all right. And then take a break, come back later, maybe a day or two later, and take the sample exam. Look at the answers, convince yourself of all the right answers that you understand, and then you will have done the most from this program in order to prepare yourself, to help prepare yourself for the RMP exam. Certainly wish you the best of luck, and thank you.